So let's get away from some of the maths that we've seen over the previous slides and take a look at what's actually involved in doing some of this modelling. The analysis process, even when we fully understand it, is complex and the calculations are involved. So ideally, you don't want to be doing this by hand. You really don't want to be doing a spreadsheet either. You want to be allowing software to do this for you. We've been going through it up to this point because I think it's important that we understand what that software is doing. And in understanding what that software is doing, we've then got a chance of altering our structure in a way that we're able to reduce the response if necessary. One of the biggest issues we've got for complex structures, which are those that don't have sort of a regular rectilinear grid layout, is that the modal parameters that we require for the analysis, the mode shapes, the frequencies, the masses, are quite difficult to come by. Simplified methods have been developed. That's something we'll look at next session as well, and they've been calibrated against this full finite element method that we've been looking at, but the range of application of those methods is far more limited to regular structures. So often it's not possible to calculate these modal quantities by hand. That's when we really need our software to do that for us. As well as being slightly more restricted in its application, the simplified method that is there for hand calculation can be overly conservative. It needs to be conservative to cover the range of cases that it's being used for. So an FE model is always going to be useful if you have the capacity to do it, to provide you with greater accuracy for pretty much all but the most simplest of structures. There are numerous commercial software packages that are capable of performing either part or whole the whole process. Typically, structural design software that you use for other purposes will have some built-in capability of doing the response factors. Obviously, different software has different strengths, so some may be better than others, but it's certainly worth looking into if you've got existing software before you go out and buy some new software, just to see if that software is capable of doing what you need it to do. The general workflow would be to create a model that is constructed out of 1D elements, which would represent our beams and columns, and these would typically be beam elements. You'd also have 2D elements, which would represent the floor or the slab, and they are likely to be some sort of shell element. The relationships between these elements are then determined using the finite element method that breaks it down into multiple degree of freedom discrete systems. And the accuracy of that solution is then going to depend on the number of elements, the number of shell elements of the floor that your system is broken down into. But you need to remember, certainly for large structures, that with increased accuracy, with more elements in your floor, you're going to have increased complexity and so higher computational times. With the model created and your elements generated, we need to do two analyses. The first analysis is a standard modal analysis, which you might have performed on your structure for any number of reasons, other purposes other than vibration. And this will give you the modal parameters that you then need to pass into the method that we've been looking at over the last few slides. This second analysis takes the modal parameters along with other user-specified parameters and performs what we would generally call a footfall analysis. The footfall analysis is going through and applying the equations we've looked at before at each node of the floor and producing a response factor set of results, which is normally displayed as a contour plot on the floor of the structure for each of the steady state and transient response factors. And sometimes you can set it up so that it displays the critical response factor at each location on your floor slab. So just to run through some general modelling recommendations, I'll use this example that I've got in the screenshot here, which is a simple model of SCI's office building that I put together in about half an hour or so, similar to the FE model that's shown in, I think it's Appendix D of 354. That was done about 15 years ago, so I didn't have access to the original model, so I produce a new one now, but largely it is similar. Aside from the opening for the staircase on sort of the top left of this model and the absence of a column in the floor area to the right, so just around there, this is a fairly regular rectilinear structure. The screenshot shows columns in yellow. We've got a floor slab in dark blue, primary beams in They are meant to be red, but I'm not sure how clearly you can see the red. That's just along this edge here. And then we've got secondary beams in this sort of turquoise colour just along here. The primary beams look a little bit odd here. They've got a gap running down the middle. That's just because they are castellated beams, and in this particular software I'm using, that's shown as a gap along the length of the beam that's equal to the height of the opening. You can see the location of the primary and secondary beams under the floor slab at these orange lines that's going through the slab there. So here I've modelled the first floor of the structure, and what we typically recommend, particularly for large structures, is modelling one floor at a time. This is mainly to reduce your model size and speed up your runtime, but also it's generally not necessary to consider the interaction between different floors. If you're modelling something such as a staircase, then obviously you can't model a single floor plate, but in this discussion we're just going to restrict ourselves to the modelling of floors.